All right, Carol, I guess we're going to go get started. I know we have a lot of content again this week. And for those of you who joined us during our last webcast, pretty unique features in version 4. So just kind of want to reiterate to those out there that have existing RSP-Z2s that are running version 3, go to our website, download the version 4 migration package free of charge, and upgrade those existing RSP-Z2s in the field running 3.0. There's some instructions there that talks about how to do that. Carol, before we start talking about the new adaptive transmit audio delay features of version 4 of the RSP-Z2, I think we should start talking about why we need transmit delay. And I got a good example of what happens if we don't have transmit audio delay. So in this example, I have an RSP-Z2 at the left and a donor radio at the right. And for all intents and purposes, there is infrastructure at the right. And this could include trunk radios, satellite PTT radios, radios that use ciphertext or scrambling or block cipher, for instance. And those types of radios are inherently slow in terms of process delays. They have to go through algorithms prior to sending or transmitting voice information over the air. So let's take a look at what happens when we do deliver inbound audio to a RSP-Z2 in example. And this could be an attached donor radio. It could be an ROIP link from another remote gateway. It could be inbound audio coming from a SIP connection, or maybe even a push-to-talk of a cellular service. And the job of the RSP-Z2 is to signal the donor radio to begin transmitting. And if we don't instate transmit delay in the gateway, we're just going to go ahead and deliver that outbound audio to the donor radio. And if that donor radio is acquiring a channel or experiencing propagation delay, if it's a satellite radio, for example, the resulting output will be truncated. In other words, the first few syllables of words will not be delivered out to the downrange radio. So here's another example of an example of transmit delay that is of a constant value. And this is something we've been using with ACUs and NXUs, particularly ACUs since the late 90s. And we can go ahead and enter a value for our transmit delay buffer inside the RSP-Z2. So same example here. We've got inbound audio. Again, it could be a connected donor radio, or it could be a stream from a remote gateway, for example. And once the information enters the RSP-Z2, we're going to go ahead and send a PTT control signal to the donor radio, keying that radio, allowing that radio to do its job, set up its algorithms. If it's scrambling, it's going to take time. It has to connect to a geostationary satellite and a downlink. We're going to give it time to do that. But in the meantime, we're going to buffer the transmit audio within the RSP-Z2. And if we do our calculations correctly and we understand the acquisition time of the channel of the radio system at the right, we can enter a transmit audio delay value that might be just slightly greater than the process delays of the radio system. And if we know that, we can then dump the buffer after we've buffered the audio in the RSP-Z2 in an example and deliver the information downrange or to subscriber units out in the field. And in this case, we're mitigating the loss of the first few syllables or words of the audio stream. In version 4 of the RSP-Z2 firmware, we can now use what we call adaptive transmit audio delay. So here's an example of what we call audio pattern transmit audio delay. But in this case, we're going to still send the PTT control signal to the donor radio, but instead of entering a hard value for the transmit audio buffer of the RSP-Z2, we're going to instead allow the donor radio to acquire the channel. But during that period, we're going to store transmit audio in the RSP-Z2, but listen to the permit to talk tone. The RSP-Z2 is going to listen for the permit to talk tone. And when the talk tone goes away, we're going to release the transmit audio from our buffers in the RSP-Z2, deliver that to the donor radio, and we can, again, mitigate the loss of those first few syllables or words of the transmitted audio stream. Okay, we're back at the settings screen of the RSP-Z2. This is the user interface. So I'm looking at the settings, particularly of the radio resource. All right, so at the bottom left-hand corner is where we adjust the transmit audio delay. And incidentally, you might have noticed that there is no adjustment for the receive audio delay. And the audio delay on the receive side is primarily there to mitigate the loss of, again, syllables, first few syllables or words of a receive stream. And that's usually attributed to the process delays inherent to the gateway or the digital signal processors inherent to the gateway. So we've already baked those values in and you don't have to worry about the receive audio delay. We do have the new transmit delay features on the bottom. As you can see, I have this originally set to none. Don't want to do that because you might need to preserve those first few syllables of the audio stream. And so it can select a constant value. This one happens to be set to 4,000 milliseconds or 4 seconds. We can go as high as 10,000 milliseconds. All right, so let me go ahead and select one of the new adaptive transmit audio delay features, and that would be, again, the audio pattern feature. Again, we're listening to the permit to talk tone while we're filling our transmit audio buffer. When we hear that permit to talk tone, we can then dump the buffer, and hopefully that radio is going to be in a settled state where it can accept all the audio and not truncate those first few syllables or words. And so I'm going to go ahead and increase my transmit delay time. I'm going to show you why in a moment. I'm going to go ahead and save that. I'm going to set it to 8,000 milliseconds. That's 8 seconds. And that might seem a lot, but we'll see how that comes into play. But before I can implement this feature, I need to allow the RSP-Z2 to learn the permit to talk tone, particularly of that supporting donor radio. So we do have a training function. And when I click this button, depending on how stringent or how precisely I want to interpret that permit to talk tone, I can select one of these features here. But once I click the Train Now button, the RSP-Z2 will key the donor radio and listen for the permit to talk tone. It'll do it maybe 2, 3, 4 times until it creates an average and is sure that that permit to talk tone is repeatable. After every subsequent transmit session, we're going to listen for that permit to talk tone. We're going to compare it to our database. And if we recognize that as a permit to talk tone, we're going to go ahead and release the transmit audio buffer. So if I go down below the transmit delay panel, I'm going to click on Advance, and this will expose some more interesting settings related to transmit delay. And this is the ability to rekey the transmitter maybe once, twice, or several times during the transmit delay period, which, as you can see, I've set to 8,000 milliseconds. Again, I can go to a maximum of 10 seconds. So this gives me an opportunity to rekey the transmitter within, in this example, an 8-second period. And if I don't achieve the permit to talk tone, I'm still at 8,000 milliseconds. I'm going to dump my transmit audio buffers and hope for the best. So let's talk about another adaptive transmit audio delay function. I'm going to go ahead and select that here. And we call that busy channel. And I've got a good example here. Let me go ahead and show you a diagram. So in this example, we still have the same components. We've got an RSP-Z2 on the left, a donor radio on the right. We still have inbound audio coming into the RSP-Z2. And again, we're going to go ahead and key the donor radio, but we're also still going to implement our transmit audio buffer. This radio system is different. It will not provide a proper permit to talk tone. Some radios will emit a constant tone, and when that tone is extinguished, that means we've acquired our channel, and then we can start talking if we're using a subscriber unit. But in the case of the RSP-Z2, we send the PTT control signal to the donor radio, initiate the process, and the radio is going to begin emitting a constant busy channel tone or a signal that the RSP-Z2 is going to listen to. And while we're listening to that tone, we're going to start filling our transmit audio buffer. And after a short period of time, the busy channel tone should subside. We're going to go ahead and dump our transmit audio buffer, deliver that information to the donor radio, and hopefully that donor radio is going to be in a settled state. And again, we're going to mitigate the loss of that first syllable or words in that transmitted stream. So we're back in the user interface of the RSP-Z2. Let's take a look at that transmit delay panel on the bottom left-hand corner. I'm set to busy channel. I'm going to go ahead and leave my transmit delay to 8,000 milliseconds. And the Train Now button is now disabled, and we don't need to train on the busy channel tone. And when the tone extinguishes, That's when we dump our transmit audio buffers and deliver the audio to the donor radio. So, and just like the audio pattern transmit audio delay mode, we can also instate a rekeying function as well. And this could be multiple rekeying functions or a single rekeying function. And so if we don't acquire the channel, we're going to attempt to rekey the donor radio within the transmit delay period. And in this example, I'm set to 8,000 milliseconds. Again, we can go a maximum of 10,000 milliseconds, which is 10 seconds. So while we're in this panel here, I want to go ahead and talk about another feature. But again, Carol, I have another diagram. I'm going to go ahead and show you that. So this is an example of two disparate radio systems, both being supported by a repeater. And I'm going to show you the path of the audio from one disparate system to the other. And when we key a subscriber unit out in the field, we're going to hit our repeater, and our donor radio is going to accept that information. We're going to deliver that information to the disparate system. And when a subscriber unit releases their push-to-talk button on their radio, the red donor radio on the bottom right also releases its push-to-talk. And if there is a significant squelch tail, or maybe even an ANI IDing tone or an MDC 1200 or any non-human audio artifact emitted from that repeater, that information is going to be sent to the donor radio. It's going to be in a received state. We're going to deliver that information through the gateway and rebroadcast, this case, a squelch tail to the other disparate system. And if that system has a significant squelch tail, it's going to be rebroadcast back to the other disparate system. And we classically call this repeater ping-ponging. And the squelch tail or that artifact will be bounced back and forth between these two systems. And really, the only way you can mitigate this is to somehow block the ability to receive that signal just after the donor radio is in a transmit state. And we call that receive inhibit after transmit. So back at the user interface of the RSP-Z2, we're still looking at the radio interface, but I'm under the audio control panel. I'm going to go ahead and open the advanced panel. And down here at the bottom, we see receive inhibit after transmit. And I've got a value set here to 4,000 milliseconds. So in this case, the 4,000 milliseconds is the period of time where I'm going to block any receive activity coming in from the donor radio just after it was in a transmit state. All right, so this is going to allow me to hopefully block that squelch tail or that anti-IDing tone or that non-human audio artifact. And so one of the drawbacks of core inhibit or receive inhibit after transmit is that we might sometimes block legitimate talkback. And this is two-way communications, and that's what radios are all about. So if I have a reply from another subscriber unit within this 4-second period, there's a chance I'm going to block that legitimate audio coming back into my system. So we've added a new function called receive inhibit recovery. I'm going to go ahead and set this to yes. I'm going to click save. And now I can use a high value, for instance, 4,000 milliseconds. And what receive inhibit recovery does, it's going to listen to that artifact, whether it's a squelch tail or an ID tone. And if we exceed the 4,000 millisecond period in my example of constant audio, we're now going to assume that that is legitimate communications and somebody's trying to talk back to me. And so what we've done is effectively buffered the receive audio and essentially recovering any legitimate communications coming in from the receive side. We can still block the squelch tail because that squelch tail is going to subside hopefully before the 4,000 millisecond time period. But if it goes beyond 4,000 milliseconds in this situation, we're going to assume that it is legitimate talkback communications. We're going to append that audio by buffering the receive audio. So this is a great feature, core inhibit or RX inhibit after transmit, but we can now recover the audio if we have legitimate talkback and still have the ability to block that squelch tail and prevent repeater ping pong. And so the last thing I want to talk about, Carol, is the ability to adjust the gain on some of our digital protocols, like in this case, a push-to-talk of a cellular protocol, or even an ROIP protocol that we see here under the audio control panel. And we can now control the digital gain coming from that digital resource. Again, it could be push-to-talk of a cellular, it could be a SIP, it could be an RTP resource. And what this allows us to do is add 26 dB of gain or 26 dB of attenuation to that signal. Essentially, we have lots of dynamic range now. And so now we can do true end-to-end gain staging. One thing I want to kind of conclude with is the MCC console type. And this now allows us to add more control to the MCC multi-channel console interfaces. And we'll talk about the MCC multi-channel console in a later webcast, but now we have lots more control as well as digital control of the gain. And again, this is primarily used for gain staging. So, Carol, I went way over time, and so hopefully this content is going to be useful. In our next webcast, what I really want to focus on more on the RSP-Z2 version 4, so I'm going to talk about the ability to back up and restore our settings of the RSP-Z2, something that's really big. This allows us even to create maybe a mirrored configuration that I can share with other RSP-Z2s that I want to deploy in a large wide area system. So
thank you, Iggy. Thank you so very much. That's very interesting. It's easy to see why we need multiple webcasts to cover all of this information. There's just so many new features in this upgrade, this migration from version 3 to version 4.
Okay, so I guess we'll go ahead and wrap it up. I appreciate everybody for attending. I believe Carol and I will hang out afterwards and take some questions, and hopefully we have some answers. And so, again, we appreciate everybody for attending this webcast, and see you on the next webcast. And please hang on if you want to join our Q&A.
Thank you so much. Thank you, Iggy. We look forward to taking their questions and hearing their comments. Thank you.